Hey, my name's Charles Priest.
My name is Kenny Sang.
My name is Benjamin Sumi, and we are Engineering Team 6, Superstart.
The task was to design a GUI. So to design a GUI, we used a guide. In the guide, we have our GUI. Our GUI consists of 3 task boxes, each with a title. One, you can choose the energy producer. One box you can choose a city, and one box you can choose a month. There are 2 graphs to output the power demand and the number of solar panels, as well as boxes to display the number of current electric vehicles, the current number of malls, current number of parking lots and apartments, as well as adding and subtracting from each of those things. So the second task we were given was to edit the green ball functions given to us in the object-oriented programming lecture. Here we have, we've changed the name to the electric vehicle. We have X and Y position as well as velocities and a radius. We also have constraints that go from -50 to 50 based on the size of our graph. We've changed the X and Y position to go all the way up to -50 and 50 also, and we've also increased velocity based on a bigger size to a maximum of 15. We have move functions which have not changed, save for changing this value to 50 so that we can extend to all sides of the graph, hit every side of the graph as we move. And we also still have the get points, which has not been changed so that we can graph this. So to call this function, we didn't change much, just inputted a number so that we can choose the number of electric vehicles we want. Here we're going to use 10. We also have a function, we have the for loop j, which defines the number of times that each electric vehicle moves, which here is also 10. So you run the move function for each vehicle, put that into a string to graph. We also have some in polygon functions here, which we'll discuss later, that will be used to collect some data. So you run this, and you get your graph that has 10 dots, each moving at random speeds throughout the graph, hitting the top, bottom, coming back. We also plotted our in polygon functions for some visual while we were working. And that's the edited green ball function.
For the next task, so we determine the number of moles. So we convert from string to a number. And to doing that, we find out the point of -50 and -50. The next point is -50 and 0. And next one equal -50 plus 20 times number of moles, and the y-axis equal -50, and then the next one equal -50 plus 20 times number of the moles. The y-axis is still -50, and then next point equal -50 and y-axis equal -50, and then that we use polygon to graph it and then determine how many EV in that region.
So once we can determine how many electric vehicles are in a certain region, we can determine, based on the data given to us in the project, how many of them are charging. J is our unit of time. So between each unit of time, we have a certain percentage charging based on the sum of how many are in there. And these are repeated each time for the number of malls, apartments, parking lots, and then at the end it is summed so that we have a total number of electric vehicles charging. After that, we can calculate a demand of power based on charging. We've determined that each electric vehicle consumes 19.2 kilowatts of electricity while it's charging. And Kenny has also written a code here to create the warning. Kenny?
If the demand is greater than 90% time the production, then it should be display the error within the 10% of the EV, increase EV. Otherwise, just leave blank, display empty.
So to decrease our demand, we simply subtract 25 EVs. after displaying the code.
Our next task asks us to determine the estimated number of V's based on the preferences that the user chose. On the GUI, you can choose the month, the city, as well as whether we use solar, wind, or both solar and wind power. For whatever you choose, it gives a specific value, as shown right here, ranging between 1 to 12, 1 to 54, and 1 through 3. Based upon these values, in the code written below, it picks out data from Excel files that we saved. To determine these Excel files, we took the data from Project 1, the solar and wind data, and converted it into the power produced at a specific time. To find wind power, we used the equation swept area times air density times velocity cubed divided by 2. And then once we determined that, we multiplied it by the efficiency of the wind. So there were a few assumptions we made when doing this. We assumed that the diameter of the wind turbine was 90 meters, and we used that to approximate the swept area. We also made the assumption that air density was 1.225 kilograms per meter cubed, and the velocity we got from Project 1. We also used 59% efficiency for the wind turbines, which was the greatest possible value that a wind turbine currently can get. For the solar data, all we had to do was just take the data given in Project 1 and convert it over by multiplying by area, and we assumed 100% efficiency. After that, we then used the given percentages at each time of day to determine how much was being produced at any given time. We determined the power output per turbine and multiplied it by however many of each kind of power producer could fit in 15% of the city's area. We do show this here, and the formula we used was the area of the city divided by the area of each kind of producer. We used the values in Project 1, which was 10,000 meters cubed for a wind turbine and 60 meters cubed for a solar panel. After this, we divided it by the EV power, which was 19.2 kilowatts, was how much each EV used when charging, and multiplied it by 0.85, which would give us the amount of EVs using 85% of the power, so we didn't use all of it. And then we used the floor function, shown right here, to give a proper number. And that is how we determined how many EVs would be used. The final part of our task was to create two graphs displaying the data that we collected. The first graph, shown right here, is going to show the time as it goes out throughout the day compared to the demand of energy caused by the EVs, and that will be a bar graph. Our second graph, which is also a bar graph, is going to show the number of panels or the number of turbines, or both, depending on which you select at the very beginning, which will be shown here, and that will be a constant number.
And the final thing that we'd like to do is show you our GUI actually running. So here we have the three boxes. Obviously, you can choose an energy producer. So let's choose wind. You can choose a city, Providence, Rhode Island. And you can choose any month of the year, say October. Could be a windy month. So you're going to start your simulation. Here you end up with your baseline. And we simulate one day with one marking the hours. So here you have the ability to change your number of vehicles, to add malls, add parking lots, add apartments, or even take them away. And that's our simple GUI. So here you end up with your bar graph. We obviously don't have much demand. We didn't have very many electric vehicles because even with 250 wind turbines, there must not be very much wind in Providence, Rhode Island. We can try and maybe get a bigger number. Let's choose maybe a bigger city in Los Angeles using some solar power and a very sunny month, July. You restart your simulation, obviously you're going to have a lot more electric vehicles. Now it's hard to read the graph because it's actually graphing directly over, which is not a big deal now because we have 10 to the 5th solar panels since our the area of our solar farm is approximately 15% of our city, and we can support almost 10,000 electric vehicles at this time. Of course, if we have more malls, parking lots, or apartment buildings, our demand is obviously going to go way off the charts, much greater, almost 150,000 kilowatts. But apparently, with the amount of sun we have, we're still producing enough. Our warning, which we'll display down here, has not appeared. So that is our GUI.